So I mean, going right back, so your equation A equals the sum of e the exponential to the power of a. So what's the little a? So that's the assembly index of the object. So that's how
Yeah.
many built Lego blocks, shall we say, were needed to produce, or how many combinations of Lego blocks to produce the object. Is that more correct?
But so the assembly index is really, you look at it in reverse. It is because what we do is we basically take the molecule or the object and we chop it up into its atoms or its minimal units. And that is a minimum number of steps you need to take. So that AI is like basically what is the number of steps I need to take to get all the way to the end. So it's always a minimum.
Yeah.
And that in reality, objects actually require more than the minimum number of steps, but this is a physical minima in the absence of any selection or evolution. And
Yes.
it's kind of, again, it kind of blows people's minds. I mean, I was talking to Sarah about like, how did I come up with the assembly equation? I was like, well, it was in lockdown, so I was talking to Sarah and I was talking to SFI. The assembly index I kind of came up with, like as I said, in 2014 with Stuart in my office, cutting up molecules in my imaginary mass spectrometer. A mass spectrometer is a device chemists and biologists use to weigh molecules and characterize them by their weight and their fragmentation. And you get fragmentation for free in a mass specs. You blur everything apart because the molecule flies into an electric field, and then to add insult to injury, you then try and chop it up and then measure the fragments, right? You look at all the different weights, and that allows you to characterize it. And that's kind of how we kind of got to the idea of the assembly index, right? Which is like, literally, if I take my jigsaw puzzle and throw it on the floor and cut, and just cut the number of different parts, I'll know how many parts are in the jigsaw puzzle. But also, not just that, when you throw the jigsaw puzzle on the floor, it might not break apart into all the individual parts. It will break apart into clumps. And if you took, let's say your jigsaw puzzle had 100 different pieces, and you take 100 identical puzzles, and you throw them all on the floor, and you allow that each throw on the floor to give you a different configuration and put them in order, you can then pile them up, right? Because you can break a different bond or break a different part, and you can put them in order and work out the assembly index. And that's literally all you do. It's really simple mathematics. It's really simple combinatorial stuff. But what it tells you is when you add another bond onto the molecule, the combinatorial space expands gigantically. And so the assembly index is really a measure of the amount of effort required or selection required to produce that molecule. But that's not enough about knowing the number of copies, because the number of copies tells you that it's not a fluke. Because you could just have one-off molecule that's really complicated, but you've only got one version of it. And so that was just a fluke, and you discount that. And that allows you to make the observation.
And so basically, your big A in your equation, that's the measure of the total amount of selection needed to make something.
Yeah. And what we're doing right now is we're showing how big A is very interesting to compare it, well, not compare it, quantify it to entropy. In the last few weeks, we can show how assembly and entropy are distinct, and how actually assembly gives you more than entropy. But the nice thing about entropy is you have a connection to energy. And one thing people are saying is that they want to understand the connection to energy. And that makes a great deal of sense, because obviously if you want to assemble something, you have to make and break bonds, and that requires energy.
Yeah.
And so what we're doing is like now showing how high assembly index molecules how much energy they need, right? How much stuff, and how many joules, and how much time to actually create it. So we're bringing together lots of concepts now, and there will be a statistical mechanics of assembly theory that's entirely consistent with, but builds on, statistical mechanics and physics, and condensed matter physics.
So remind us what entropy is there. Our listeners will have heard it many times, but in this context, so energy's cool. So you get energy, and you got your assembly index, and how does entropy, and what is entropy, and how does it fit in?
Yeah, so entropy is a very interesting idea, and I'm not talking about informational entropy. We'll talk to that in a bit. Information's a bit weird, and people misuse it. So if you're talking about, if you have entropy just literally tells you the amount of disorder or the amount of order. So basically, if I have let's say I have a crystal, and that crystal is salt, sodium chloride. If that crystal was perfectly ordered, i.e., every just sodium chloride, sodium chloride, sodium chloride, the perfect glass. Okay, you'd say the entropy of that crystal was quite low. If I was then able to go in and take a chlorine atom, a chlorine ion out, and put it on the outside somewhere, I wouldn't break all the charge. I'd make sure it's still, neutral roughly or extended, and I basically just put defects in. It would have the entropy would go up because there's more disorder, because there's more ways of arranging it. Because if you've got a perfect crystal, the atoms only have one arrangement. Right? If I have now a crystal with lots of defects in it, there's lots of ways of arranging those around. And so what you can do is then say, okay, I'm going to create kind of account for the amount of disorder. Now, that's the microscopic interpretation. What actually happened was that it was done the other way around. When Carnot was looking at heat engines and looking at difference in temperature, the concept of entropy was born out of how we looked at useful work. And I think that was super interesting because now we have the molecular interpretation of entropy, which is of course correct because we sum it up and understand that. But there is kind of like the concept of entropy from thermodynamics, heat engines, steam engines, then understanding that we had things called atoms. And actually Boltzmann, who came up with this, with basically his equation is S entropy equals K log W. And K is the Boltzmann constant, and natural log, W is the configurations, right? Number of different configurations. That Boltzmann actually was ridiculed, far more than I have been ridiculed for the Nature paper, by the way, at the time, because people didn't believe in the atomic interpretation of matter and said, no, you're wrong. And actually, poor old Boltzmann took his own life, right? And on his tomb, he has the entropy equation. Now, there's another interpretation of entropy that goes into Shannon information.
Yep.
And literally, Jean von Neumann, and Shannon just made it up, right? And they said that we call it Shannon entropy because it sounds good. And this actually was kind of funny because there is a connection between Shannon information and Boltzmann entropy, but only when you have a human being, an encoder, and labeling things and unlabeling. And this is where there's a bit of a mess in Shannon entropy, because Shannon entropy is all to do with communication, and if something is information or not. And this is where the world of physics and information theory and complexity theory got themselves into a bit of a pickle with definitions. They're still there, and they're still going to argue with me about it. But as all I care about is I'm a chemist. I burn things and I measure things, right?
Yep.
At the end of the day, I can label them. But anyway, you asked the point of what is entropy, so I've answered that. Now, what is the difference between entropy and assembly? Well, entropy is kind of the thing you get left when you remove all the causation. So it's still a quantity. So it's basically flattens the disorder of the process, if you like. So entropy plus causation plus the path is assembly. And so what we're really doing, we're showing how assembly and entropy are nicely connected. And so, and that's really gratifying because it's really starting to say, look, the assembly index is telling you something interesting about a configuration of a molecule. You can apply entropy to that, but people were tempted to use Shannon entropy, but that's incorrect because the way you label it, and the right way of labeling it, or the right way of doing it, is via assembly theory.
So I mean, if I could put that in a go for a real lay explanation, you can tell me whether this is right or it'll definitely be simplistic. But if we say that entropy, particularly in chemistry, is tending towards disorder or less order, is that what you mean by saying that assembly is sort of the flip of that? Because something is building order into these structures, or order is appearing in these structures because of causation or natural selection, and that is tugging against entropy, which should be telling us that we should be getting more disorder. These molecules should be breaking down. They should be decaying. We shouldn't have them around, but yet we do.
Yeah, now this is a really hard point that I don't know the answer to yet, but I think it's going to... So high A isn't just about order. It's about copy number and complexity. And what is weird, it's even more than that. So a perfect salt crystal is evidence of selection, because
Yes.
you wouldn't expect to find defect-free salt. There's always got to be a defect somewhere, right?
Yeah.
Right? Equally, if I made a salt crystal and I took I put the defects in identical positions, so I can maybe write Lee. Let's say I took a salt crystal. You get these pieces of glass where you can write a name in there and holographic. Let's say I got my salt crystal and I wrote Lee in the crystal so you could see it, and I made 1 million of those. You wouldn't look at that and go, "That's got defects in it. That's just random." You're like, "Someone's written Lee in that salt crystal."
Yeah. Yeah.
So
There's a process underlying.
So exactly. So what assembly does is it tells you about the amount of causation required to make that object, and the more identical copy numbers you have. So, and as entropy doesn't capture that. Entropy just says disorder, disorder, disorder. But actually, what assembly says is, no, it's not disorder, disorder, disorder. It's like kind of cool disorder, because that what looks like disorder to you is not disorder. So to the entropyist, there's disorder everywhere. To the assemblyist, they're like, oh, but that's not disorder. They are copy numbers of that. And so it's the way you count things and the way you remove the causation. And I think that that's really what's fascinating. Now, there is a tendency to disorder that we talk about.
Yep.
But I don't even know if the second law, I think it was Max Planck who said, and Einstein, and all of them said, there are many things you can break, but if you break the second law, your theory is doomed. I don't actually think that's right. I think that there is no real proof that the second law of thermodynamics is a universal law in the universe, because we've got some confusion. And it's maybe outside this podcast, but maybe it's not. It's a confusion about the origin of the universe, right? The initial conditions. Was there order at the initial conditions? Because there's the problem with the initial conditions. If the initial conditions of the universe are what controls everything, then all the complexity we have in the universe, including the books on your shelf, the configuration of lights in that building, were all encoded at the initial conditions of the universe. That's baloney. There wasn't enough density. There wasn't enough ways of encoding the initial conditions in the initial conditions. Sorry, there wasn't enough ways of encoding the future states of the universe in initial conditions. So labeling initial conditions and say entropy increases, that doesn't make any sense. And what we know, though, is in that unguided system, if you burn stuff, you get dissipation. That dissipation of useful energy to non-useful energy. But you think about it, if you take thermal energy and you add on constraints, and assembly theory would say constraints are what you need for memory and selection, you can funnel that thermal energy into something useful, like electrical energy or rotary motion. Indeed, that's what we do. Take a saucepan, put it on a fire, put water in it, boil the water away. Okay, put a lid on it, lid bumps, and go, actually, I'll change that into a piston. Piston goes up and down. Piston goes up, relieves the pressure, goes down again. That then you convert burning. Yes, there's some cost to that, but actually we have this very interesting interplay. So the physicists say the universe, is governed by the second law, and the second law says that things will dissipate and tend to disorder. But that is a macroscopic observation we make on some systems, and we observe that physical systems never break that second law, except living ones that break the second law all the time. But then we say, but it's fine because they need food and need this. And when you do all your count balancing, the second law is still, there's a cost producing biology.
Yep.
And I'm kind of sympathetic to that. I'm not some kind of heretic who say I'm gonna basically go faster than light, find interdimensional aliens, and give you a free lunch. But all I'm saying is we don't really know what time is right now. We don't really understand the initial conditions. And assembly theory is meant to say, well, assembly theory allows you to find selection in the universe from non-selection. And by the way, everything that's interesting in the universe has undergone selection. and we should probably do more with that. And so I think that the paper really has kind of opened up so many doors across so many fields. It got quite an interesting set of responses from all that. But anyway, let me just summarize what it said. So there is a deep connection between assembly and entropy. Of course, the process of assembly selection requires energy and matter, and there is a waste component, and there will be able to use statistical mechanics. But the nice thing about the key difference between assembly theory and statistical mechanics is assembly theory requires you not to do coarse graining on the causal structures. Those causal structures need to be propagated. And when you coarse grain, i.e. you just basically count the big things rather than the small things, you lose information, and that's really what the battle is about in complexity. And what a lot of people have done in complexity science is just said, I'll just measure the Shannon entropy for that. And I'll just look at the Komogora of complexity or something like this. And that kind of gets you into the wrong kind of frame or the wrong ontology for designing experiments.
And I mean, it's a really interesting idea, isn't it? I mean, it's almost like sort of saying, yeah, things are tending towards disorder, except when they produce something that actually is robust and stable. And assembly theory is kind of, well, let's go and measure how much robustness and stability was built into this thing to produce this complex structure here. So you end up with this number that is the measure of the amount of complexity, if we can use that term, inside a particular object. And then that obviously can, as you say, be related to entropy. For a lay listener, what is the value of knowing that number?
I think you want to know if the number is high or low and what the rate of change is. So assembly theory was built an idea to measure if something is a product of life or not. Why is that important? We want to find life elsewhere in the universe. We want to know what life is. Because we can't define life. There was this big argument. Everyone was like trying to define life. And I was like, let's just measure it. It's a bit like consciousness. We're all arguing about consciousness. Why not just measure it? But that's another podcast, definitely for another day, not today. I have to write another controversial paper and then get everyone complaining. So measurement here was kind of important. And for the lay listener, it's really about, it's about identifying interesting objects in the universe, what life is, what technology is, and also how to basically start to think about how we build infrastructure. Assembly theory works for genes, it works for technology, it works for economics, it works for poetry, it works for... What do I mean by all these things? I'm saying, well, you can take these systems and you can quantify the amount of information or the amount of causation required to write the book, produce the poetry, produce the machinery in a minimum way, and then therefore identify efficiencies, right? Because what assembly theory says, like, look, how can I make this molecule as efficiently as possible without dying? Because that's what selection does, it's like, almost economic systems. How can I produce this good with a minimum amount of resource so I don't get outcompeted by my competitor? It's a very similar process, and indeed that happens in the ecosystem, right? How does a predator outcompete other predators? And so it's very important for us to kind of be able to characterize selection as a general phenomena. And also I would say that the selection and the emergence or the increase in complexity are intrinsically related. In fact, I said at the beginning of our discussion, complexity can only be measured by the amount of selection. And that is, I think, a fundamental new statement I'm trying to make. Does it mean that all the complexity measures that computer science use are wrong? No, of course not. They're great. They're used in computer science. What I'm saying is, outside of computer science, we need to understand, how do we compare the complexity of a physical phenomena? Well, first of all, you say, what's the copy number? Right? What's the number of parts? And then that allows you to start to understand the amount of contingency, if that was naturally arising, and also robustness. If you look at the spot on Jupiter, that storm, it's very complicated. There's lots of moving different parts. It's a vast storm system, probably the size of the Earth, and then some more.
On Jupiter.
Yeah, it's probably not complicated in the far as it's undergone evolution. It's just the turbulence, it's just convection currents, right?
And
You know,
and near the beginning, you were saying there seems to be this sort of cutoff number on the assembly index of when we move from something that we would say not alive versus something that we would say alive. What's that?
so yeah, so I mean, the number is 14 to 15, but I mean, I think the way we can put that rather more precisely is to say the way we're measuring living systems right now is an organic. The way we've done it in our measurement is organic chemistry. We look at molecules.
Yep.
So if I look at molecules in the environment, why is there a big cutoff between, say, like abiotic molecules and biotic molecules? Of course, biology can make molecules with a low assembly index. By the way, it goes all the way down to the lowest and highest. But it's just that biology is the only phenomenon that can go above the threshold of 15. So when you immediately find a system that has got producing molecules above the threshold of 15, you know that there's a genetic system at work there.
So it's got memory and replication.
Exactly.
Yep.
Yeah, and that number comes about as just the combinatorial space, because when you move from assembly index of say 1 to 2, 2 to 3, maybe all the way up, is the number of possibilities that opens up. And so when you're going up and up and up, the space becomes so exponential, so large. When you get hit an assembly number of 15, assembly 15. So in chemistry, we have a thing called a mole. A mole is Avogadro's number of molecules. So it's basically you want to compare a mole of elements, right? It normalizes molecular weight and number. So the mole is a special number. So it's 6.022 times 10 to the 23. So water has a molecular mass of 18. That's 2 protons, 1 each. Oxygen 16, 18. Just so happens that the density of water is 1 gram per mil, and if the weight of water in molecular weight is 18, then 18 milliliters of water. Here's some water here. It's more than 18 mil. In those 18 mil, there's 6.022 times 10 to the 23 molecules. Right.
Yep.
So that's good. Such a number. So if you were to take a random walk and say, right, I'm going to take a step, and then add a bond. And then I'm going to take another step and randomly add a bond, and randomly and randomly and randomly. Once I get to 15 steps, there's a mole of outcomes. Within that 15 steps, with a common set of building blocks, you end up making more than 6.022 times 10 to the 23 different molecules.
Wow.
So the chances of you in those 15 steps making one molecule is 1 in a mole. So if you find 10 identical copies or 1 million, you're like, oh my gosh, something biased that process. So that's kind of that kind of gives you the counting, and so that is kind of very interesting for the transition, the threshold. And what that says is, look, the combinatorial space of organic chemistry is very big, and life can operate in a very privileged space. Combinatorial space of organic chemistry, and you can see the difference. And there are people who have been arguing with me about assembly indices of things you can't measure. So someone says, assembly index is not a measure of life because look, I can make this object that has an assembly index more than 15. I'm like, yeah, but can you actually measure it with an experiment, or did you just arbitrarily divide it up? And they're like, because assembly theory, again, if you can't measure it, it doesn't exist, right?
Talk about that for a couple of moments. So this is not just a theoretical exercise in terms of producing an equation. It comes from cutting up molecules in the lab, and talk about that, Lee.
Yeah, so there's kind of when I thought of the thought experiment, I was like, oh my gosh, I can actually go and do the measurements. And then that's why we started to do the mass spec. So for the original paper, before the Nature paper, we published a paper in Nature Communications, where we took samples from bacteria, fossils, all across the kingdom of life. We took extraterrestrial material given to us by NASA, and we also took soup experiments, like from prebiotic soups, and we cut them all up in the mass spec, and we just profiled them. And so we were then able to see that threshold come out in experimentally. And the way we did it is, of course, there is an equation that gives you assembly index for a molecule, which is you draw the molecule and you can cut it up, and it gives you a number. And I was like, I bet I can measure that. And my group were like, no, you don't be able to measure that. And then we did the mass spec, and roughly speaking, in the mass spec, the number of fragments is equal to the assembly index, kind of. There's an offset. And what we did, we took 10,000 molecules, cut them all up, and where we calculated the assembly index, so we just wrote down the 10,000 molecules, calculated it on one hand, and then went to the lab and then basically did the mass spec experiment and measured them, and we got a nice linear plot. Of course, there's some noise here and there. I was like, well, that's cool. And then I thought, well, I'm going to do another experiment with a different technique. And this technique is called infrared. And infrared spectroscopy is really good for molecules because the bonds basically absorb energy in the infrared and they move around. It's like heat. But the nice thing about infrared, every different bond has a slightly different energy. So that means so if you have 2 different bonds in your molecule, you have 2 bands in your infrared spectrum. If you have 10 different bonds in your molecule, you get 10 bands in your infrared spectrum. And guess what? If your molecule has 2 different bonds, the assembly index is 2. And if you have 10 different bonds, the assembly index is 10. And everyone's like, no, that's too obvious. They go work. And then we did it, and you just count it off.
Wow. So in one case, you're measuring the number of parts, and in the other place, you're measuring the number of connections between the parts.
Yeah, exactly. And then there's another technique called nuclear magnetic resonance, where in an organic molecule, you have a thing called spin, like all the atoms have magnetic moment. But of course, because they're all connected together, each magnetic moment is slightly different. And so you have a really sensitive detector, really sensitive compass, and you can measure the different magnetic moments. And of course, so I took a molecule that had 10 different parts, put it in mass spec, you get 10 fragments. I put it in the infrared, I got 10 bands in the infrared, put it in the NMR, and I get 10 NMR magnets, 10 magnet. And so we were able to get all these 3 different measurements and show that you can measure the assembly index using 3 different techniques that have no connection and correlate it with a theory. And suddenly people are like, oh, okay, maybe that you can really measure this and it's a thing.
And so where to from now? So you can measure the number of bits in it. Where do you go now with the research?
Right, well, there's so much we're doing right now. We are using assembly theory to measure, to quantify the tree of life without using genetics. We're applying assembly theory to genetic theory to basically understand genetic sequence using this minimal approach to saying how we can move the genes. We are looking at the assembly theory of inorganic minerals to understand how minerals help organic chemistry become biological, because minerals don't have a big enough combinatorial space. We are also looking at the transition, and this is a lot of work. All this work is I think is now Sarah Walker's team in ASU are doing a lot of the theory, and also looking at the physical consequences of the theory. And my group are doing experiments and some theory, and then we're kind of mixing up together where Sarah's team are also doing some data-driven experiments where they're getting data. So it's kind of funny that Sarah's team become experimental and my team becoming theoretical, but we're kind of all mixing up just from different perspectives. Because her group is one of the physics and astrobiology, and my group is one of the chemistry and complexity group. And then we're looking at the phase transition, because there must be a phase transition assembly index and that mechanism. And a lot of people have been asking about, with the paper, say, well, what is the mechanism of the getting to beyond the phase transition?
This is the phase transition between life and non-life.
Yeah. And I'm like, that is an important question. In fact, it is the question, and we think we have cracked it. And it basically is what you need to do to turn life into non-life is the following. You need to have some time, obvious, some energy, some building blocks. However, if you have building blocks, you can generate an assembly space. And if you have enough time and you have enough energy, you get self-replication or autocatalysis emerges in that assembly space. And what we're doing right now is we're characterizing the changes in the environment required for robust replicating assembly spaces to emerge in the environment. And that's what we're doing right now, and modeling that and putting numbers on that, because what that will allow us to do is say, what is the likelihood of origin of life elsewhere in the universe? Where should we look for life? Can we make new life in the lab? Can we generate new technologies using evolvable tech? And so there's lots of different strands going on simultaneously, and also we're writing a kind of an assembly theory for all the disciplines, so people can come from different disciplines to look at it and apply it. And we're also writing a kind of a philosophical perspective, which just basically gets the definitions right and allows people to discuss with us. Because in the paper, I would argue the paper caused discussion because people wanted to make sure the words we were using, they understood the meaning. The problem when you do something new, if you make up new words, everyone says you're being pretentious. If you use old words, everyone says you're being confusing. But all we did in the paper is basically say that selection does not belong to biology. Selection occurs before biology, and evolution is not confined to biological systems. That evolution, the process leading or selection that drives evolution, occurs before biology. And that's logical, because otherwise, how do you go from sand to cells in 100 billion years without having a creator?
So talk about, just to finish, the controversy. Tell us about because I mean, I was following it, and I mean, this really was controversial. It got very exciting.
Why didn't you pick the best controversy? Because I think I just avoid the most. What ones did you find? And we can discuss that.
Well, I mean, the bit that my impression of seeing the controversy was probably a little bit harking back to what you said earlier. It seemed to me a little bit less about assembly theory itself and more about just statements you've made in the paper that seem to upset everyone. And I heard you on Lex Friedman, where he just went through the first two lines of the paper, and how even like that just upset people straight off the bat. Is that your impression of it as well, or am I missing a whole suite of legitimate criticism in the middle?
So I think there is. So people had some comments on the phrasing in the paper. We cover that, and then there's a very small minority of trolls that I don't want to give much airtime to.
Yep.
I won't mention them, but I will actually mention what they're doing, and it's kind of funny. So let's talk about the paper. Yeah, the paper was it was a bit of a social media riot. You get this a lot where people were dumping on it and saying, and also I wonder if they were dumping on me, because I have a certain social media presence, right? I'm relatively direct in person. I'm direct on social media. I think people take themselves too seriously. So it's kind of funny just to poke, right? Because it's, and I don't mean it in a obnoxious, unprofessional, rage-inducing way. I just think it's quite great to get people to think, but going to the paper, so I think a lot of people just copied each other because they thought it'd be cool just to beat up, because they're beating up on me. But what we didn't understand is they were beating up on the first author and my collaborators, so Sarah and her team. And that was kind of a bit silly, because Sarah and I worked on the paper pretty much, in hand, right? So the first two authors, so particularly Abhishek, who was the first author from my lab working on it, did a lot of work, really dedicated individual, very smart guy, quite skeptical of assembly theory himself, right? When you're doing the science, you're skeptical of what you're trying to explore. You're playing devil's advocate. And the second author, Daniel, was from Sarah's group. And then we had Chris Kempe and Michael Lackman from the Santa Fe Institute. And actually, what happened was that Sarah and I were working with Daniel and Abhishek. And then during lockdown, I was meeting with Chris, Michael, and Sarah every Friday, going through this. And they were like asking questions and prompting things. And they were really friendly skeptics. They're like, but what about this and this and this? And we argued about it, and they got it. And they were like, oh, this kind of works. And I realized when we were getting the paper that these were the authors, right? They actually contributed to the work, the way that we shifted our thinking. And that paper we wrote, we started off, we wrote about 40 versions of the paper. And then we decided to start again. And then we then went through 120 versions. I think there's 160 versions of that paper. And so when people went, it's so badly written, I was just like, sure, you should have seen, there's a lot of stuff in there. So the first line was like talking about, evolution and physics, right? And saying people have grappled with the kind of the creativity of evolution, but the kind of the way that the initial conditions of the universe. And we were just trying to say two important things, or maybe three, but two main things. First one is the initial conditions and the idea of evolution don't seem to be consistent, right? Now, physicists will argue with that, but it's not true. If you take the initial conditions should predict the evolution of life, but they don't. But it doesn't.
And the initial conditions, you mean like the Big Bang?
Exactly.
Yeah.
Yeah. The core understanding of the Big Bang. The other thing is that the biologists talk about evolution selection, but what about before biology? You suddenly didn't just get to a cell and suddenly, here's a cell, let's evolve and select. And so there is a thing called selection that occurs in the natural environment. Selection is the process by which the environment acts on something. And if you've got a number of objects and after a process, some objects are gone and the other object is there, you can say by that measure that semantically A was selected in favor of B.
Yep.
For me, that's perfect, right? And then evolution, it then is about the development of causal structures that can survive in an environment where there is a prospect of death and survival and needing variation. Now we know that in biology there's so that was that. So I thought it was kind of funny because I actually thought all that insult and argument about the paper was actually totally over the top. But I then realized actually it's not a problem. It's been published in Nature. Everyone's talking about it. I had 100 times more people telling me it was interesting. To me, no one come up to me and say it was not interesting. They was just kind of, ranting. And so I wonder if when you do something that's kind of gets people to think, you're always going to have a loud minority, right?
Yeah, and I think as well when you, I mean, one of the common themes that we've seen from talking to people on this podcast is that when you do something that is, spans disciplines and steps into very specific areas of science, shall we say, like for example economics. If you're doing something that goes in there but also goes into biology and those sorts of things, that does seem to cause lots of controversy in terms of people going, well, hang on, you have no right to be in my space talking about this thing because you don't know anything about what I'm talking about. And we've had that with Brian Arthur. We've had that with many guests talking about you put out something that's a little more interdisciplinary, and you do get told to get back in your box a little bit. So it's a very consistent approach, I would say. What do you see here?
Yeah, and I think what happened was there were kind of 4 or 5 fields that said exactly that: get back in your box. And then also they all said it was so badly written, it was too confusing. But yet, all the generalists who read the paper loved it and got it and went, oh, that's amazing, get the copy number, get to see it here. So it seemed to me that if you're a dogmatist, you're going to hate the paper because it's challenging everything you know about your subject, causation and all this stuff, and you're going to hate it, you don't understand it, you don't think it. But if you're open-minded and you read it, you get it. So I kind of think that was cool. I really like that. So that was kind of like the gatekeepers and the generalists read it. But the nice thing about assembly theory was born in a set of experiments that found some regularities in the universe that are allowing us to ask, excuse me, what is the phenomena of life? What is the difference between living systems and non-living systems? And forgive me, I'm going to swear, but not very much. It's like I was talking to some guy about this who does Mythbusters, and I was explaining it to him. I think his name's Adam Savage, right? I hope he doesn't mind me name dropping him. And I was talking to him about this guy, and he says, so what you're saying is life does non-random shit at scale. And I'm like, yeah. He's like, that's cool. I get that. And that's kind of what assembly theory does. It quantifies the fact that life does non-random shit at scale, and we can measure it and get back to the beginning.
But let's finish on another note. What does, by the time you retire, what would be the dream of where you'd like to get to with assembly theory?
I mean, I don't really have. I want to keep asking. I mean, I've only just asked one question. Why? I would love to basically establish. I guess I would like to shift our scientific paradigm a bit. I'd like people to understand that life does do non-random stuff at scale, and maybe assembly theory is pointing to a new direction to think, and that would be great. I don't think I'm going to retire. I think if entropy does exist, entropy is going to retire me at some point. But I would say that there are 4 really important questions that go together. There is the origin of life, that phase transition, number 1. There is the origin of, I would say, what I call it, intelligence. Or something like that. What intelligence is? Let's call it. It's a bit like information. When living systems start to use sensing to gather information, it's like some kind of intelligence, not just instinct.
Agency? Would you call it agency? Or?
Yeah, kind of. Yeah, agency and instinct together. So you got instinct and then agency. Instinct comes before. So origin of life, origin of agency, origin of abstraction, and then origin of consciousness. And I think all those problems are basically the same problem. And as I alluded to, is that selection drives them all. Because selection turns random matter into evolving matter, right? Then evolving matter can only evolve over a long time. It needs life and death. And what evolving matter does, in addition, when you start to have animals and things that move around, you have instinct. And instinct are traits that have been produced over many generations, which I would say are really not, you do get from sensory inputs, but they're not, there's no underlying ontology for that instinct. The instinct is basically over many lineages. And then from that, you break free of that instinct when you can start to abstract and go, oh, why is that, why is that, why is that? And that you need some kind of labeling scheme. And that's when abstraction comes in. And then you need language, and then intelligence, and then consciousness. And what consciousness does is consciousness allows you to do counterfactuals in your head. So I can imagine doing this. I think, well, probably that's not a good idea to do that. I can do that. Or I can make this rocket, or I can make this computer, or make this drug. And so you can think about those things in your head and go through lots of different things that you would normally in biology just have to do, because you are a victim of your assembly space. And what actually happens is consciousness is almost like a holographic assembly space adjacent to the physical space where you can play around and not have to commit your stuff to real action. And I would say one day, I think we're going to measure consciousness by the number or by the size of your imagination. And I think that, but that's my real project coming next. And I need to actually, so what I would love to do is I'll have assembly theory to basically get the phase transition, show that the selection is a fundamental phenomenon in the universe, and it produces all the interesting things that we have in the universe, the information in it, and then start to use it to see if we can develop new technologies, find origin of life elsewhere, aliens, and so on. I think if we could actually use assembly theory to identify the right conditions for life elsewhere in the universe, point the telescope there and find life, we will be able to use assembly theory to unequivocally say, oh, that thing is complex at scale. There's no way that's a natural phenomena. Therefore, that must be a living system. That's going to take a long time for humanity to even agree with that. And I don't want to spend the rest of my life just trying to bash people into it. My job is to ask why, ask us interesting questions, develop technologies, and run with it. And so, I don't know if I've done anything interesting yet. I'm interested in it, and I'm really privileged to have worked with great collaborators and very fortunate to have had funding and people that want to work with me on it and ask questions and develop it. So for me, the process I'm going through right now in my assembly space is more than enough. I'm living the dream.
Lee, thank you very much for being on the show. It's been an absolute pleasure.
Thank you for your questions. It's been great.